in India, and good morning for all the people that stay in Brazil or in other zones. So I will try to be I will try to make a presentation very simple, very driven. I know that this is a web seminar that would be more would take more time, but we don't have too much time, and so I will try to pass in just 1 hour, about 1 hour, all the workflow concerning a basin evaluation since the data loading, the G&G data loading, until the prospect presentation to the manager, to the exploration manager. So it's very tough, and so I try to make it simple. And so I will start here to present what we got. So the course outline is geological, geophysical available data. We can start first to talk about it, and then we go through the G&G data loading control. That's very important for your basin and prospect evaluation. So, and then we go through to the build up of the seismic project, load everything, perform the seismic interpretation, and then we go through in the end to the prospect definition, and then match with the manager view. And so this is the basically the main outlines that I will talk about it. And then here we have a pyramid of all procedures concerning this workflow. At first, we have to take care about the G&G, the geological and geophysical available data. This is the base. This is the base of the pyramids that we have. This is the foundation of your house. This is the foundation of your residence, your project. Because if you don't have available data, you don't have nothing. You do, and so you have to take care what the data you have. And so we can go through. We can go through with the G&G data loading. That's very important because sometimes in my career, I saw some well displacements, wellhead displacements, and so seismic lines displacement in another geographic region. And so sometimes a messy loading give more trouble and take off your short time to present a good project to your manager. So sometimes you have to take care with that. I saw so many displacements or data displacement in my career that it took a lot of time sometimes in some projects. And so you have to take care with that. And so I will show you in a fast way to try to control the loading of your data. It seems to be is not important, but it's very important because a good geophysicist and geologist do not just take care with the seismic interpretation. They take care with everything. Since the loading, since the gathering of your data, and then how you're gonna present it to your manager. And so you have to take care about everything, about economic factors, and so volumetric factors. And so you have to show a economic prospect to your manager. You cannot show a small prospect, and so you will say, okay, I don't care with your prospect, your lead, and so you will waste time, and probably you waste the time of your manager. And so this is very important to the foundation of your project. So the seismic interpretation, you have to take care what you are following, which the horizons you are following. If you match with the seismic phases that you're seeing, and so it's I will show you properly how to follow very fast. And so at last, the prospect definition and the match with the manager view. after the prospect, the volumes calculation, the risk analysis of your prospect, we'll talk about the way to show to your manager. And then the main goal here is to put everything in shape. The workflow is that one. And then the final goal will be the peer review that will analyze your prospect. That is, it's away from your office, and so is the end of your work. And so they will start to revise your prospect to judge the prospect will be approved or not. And so a decision tree will be made, and then he will be ready or not for bidding. So this is the main goals, but all the activities regarding the geologists and geophysicists, our job is this one here, from the foundation to the prospect definition and match with the manager view. This is our concern here. After that, this is the following issues that the goal will be here, but our workflow is exactly here, okay? We have to keep this in mind. And so, as I was talking about before, the most important is to control the data, the G&G data that you have, the geological and geophysics data, physics data that you have, in order to produce a reliable and consistent basin evaluation and prospect definition. So if you start to grab a lot of piece of information that you doesn't know where you got, if you don't have any reliability, and so you will be just put garbage, more garbage in, garbage out. So this is the essence of the work here, to take care since the beginning what you're doing. Because if you put too much garbage, and when you go to the last step is to show your prospect to your manager. When you see that you got some displacement, well displacement, you don't load properly the seismic line, you don't match properly the different seismic vintage. So if the manager will see this displacement, he won't go through. You will lose your reliability, the confidence of the data, and so you lose a huge amount of time. So take care with that. This is the first rule, okay? So the main reference that we have for the leads and prospects is for sure the available G&G data. We must know the orange of this data, the seed, where they come from. If the geological or geophysical data came from, for example, with a national data bank, that's pretty good. Or if they got with a bid round data package, a bid round data package, okay, it's pretty good because it's concerning a well drilled in the basin, and so it's something physical and reliable. But sometimes you can go through to a scout data, for example, some websites that technical and reliable websites such as EHS, Wood Mackenzie, that sometimes performs a pretty good technical and economic reports. So normally Total uses Wood Mackenzie and EHS. Some companies such as Repsol or even ENI normally uses EHS, but basically this is one of the most important scout data and technical and economic reports that you're gonna find. There is a bunch of them, but this is an example. EHS Wood Mackenzie, that could be that some board of directors of some oil companies know, some exploration manager know, and everybody know what is EHS Wood Mackenzie, or even so you can purchase the legacy data from CGG or PGS and other seismic acquisition companies. So this is the control that you have to make. No way your exploration manager will help you to purchase because he will control the budget. And so we have to take care with that. Okay. So on this issue, if you have a field data or lack of reference, this became a huge risk. You will aggregate a huge risk to your project. So take care with the lack of reference. Sometimes you could have just one seismic line. Sometimes you have 2 or 3 legacy old seismic data, but you have to take care. You have to try to match and load properly, because if you saw just one anomaly in a seismic line, if you know exactly the origin of this data, the polarity, the kind of amplitude relate to that data, you can convince your exploration manager to buy way more seismic data or buy more data. And so sometimes the manager has a limited budget. You have to convince him, okay? If you have a good control, as I said before, if you have a good control, everything becomes possible. In Repsol, I remember in between 2007, 2008, our team in Campos Basin in Brazil, we start to define a lead, a prospect with just one seismic line, a legacy seismic line. We saw one anomaly over a high. And so we explained, okay, it's a negative anomaly, it's related to a reservoir. And so we defended it to our manager, and then they purchased more, 2 or 3 lines over this anomaly. And we started to build up a map and follow this lead. And then we defined a prospect that was approved and successful prospect, called SIAT in Campos Basin in between 2007 and 2008, when and Repsol got this lead and was a successful bid round. And then is an example that if you have just a good line, a seismic line, you can try to convince your manager buy way more data, okay? Sorry. And so this is the beginning of everything. When you set up your seismic project, the data loading control, at first you have to know where is located your region. If you are located in Santos Basin, for example, here, you have to set up your project in UTM 23 South, that is below to the Ecuador. And so we have to keep sure that which kind of projection we are gonna use. If you're just working in Santos Basin in Brazil, UTM 23 South, and a Brazilian datum that could be Sirgas. And also, if you work in a Campos Basin that is very near, is UTM 24 South, for example, Sirgas datum. But if you are in India, most part of you work in India, in Indus Basin, that is close to here, is about here, you normally use UTM 42. So you have to take care, everybody knows that if you work with some basin, you have to work with a projection, okay? If a local basin projection, more or less, you normally use UTM, okay? Universal Transversal Mercator, okay? Mercator, okay? This is an example here. This is a 23, 24, and then 25, and so near here you have 42 here, for example. You go here to the north, and so you're here in lower Indus Basin. For example, here, when you start to load a project, when you start to create a project here, you will set up properly. This is Petrel software. It doesn't matter which software that you gonna use. It doesn't matter. All the softwares will follow the same rule. You have to create a project, set up the projection, and start to load. This is an example using Petrel 2017. So here you will input the UTM, the coordinate system, and so you will select here, and then you will start to set up your project area. So this is the first thing that you have to do, okay? And then after you loading your seismic project or define your projection, you have to put some geographic reference in order to see, okay, we are in good shape, we are in good reference, because you have to set up country outlines, borders, water depths, lines, and so political outcrops in order to define and locate your project. So the shape files is very important. The geographic reference is very important. Normally the shape files came with a file with, call it .shp. So the shape file, and so you load first this political and the country outlines, the bathymetry lines, and so after that you start to load the wellheads, okay, and then you load your seismic lines, okay, and then you have everything in your project, all the reference and in there, okay. This is an example of using Petrel in order to load the shape files, okay. You go here, and so you select a new folder, for example, and then you go through you import, click on the right button of your mouse, and so you will import the file. And you go through your data set, and you will select the shape files in order to load your reference, your geographic reference, okay? So after that, as I mentioned before, you will start to load your wellheads. And so you click on a new folder, browse here, or you can load just well per well, or you can load several wells all together. And so you go through the same way, click on the right button. Okay, sorry. So right button, and so you will select the wellhead, and simply is an ASCII file. You have to select the ASCII file, the function XY, because you will build up, for example, the well name. You put a well name, for example, an ASCII file. You put the XY coordinates related, the total depth, and also the calibrage here. This is a standard file in order to load your wellheads, okay? And then after loading the wellheads, you need to load also the logs, the well logs related to each wells and the markers. So the same way, after you load your well, he will be here in the input here of the Petrel, for example, and then you can click with the right button, import file, and so you start to there is an option called well logs, last files, or the lease files, and so you start to select the well curves, the suite of well curves that you will gonna load. And so select one here related to well 2 here, well 2 select, and so you load this way. And after that, you go to well tops the same way. You put a folder the same way, you select, and then your function XY ASCII. And so you put a file, an ASCII file like this, the name of the same well, the formation, for example, the tops, okay, the in meters or feet, it doesn't matter. You have to set up the unity of your project, okay? And then the most important is to load the seismic data. That's very tricky sometimes. And so you have to previous to load everything of this your SegWit data, you have to watch the data that you have. I will explain the details now. For example, the SegWit files, the seismic lines can usually always, in a .seg format that's defined by the Society of Exploration Geophysicists, and all the trace, all the lines is in this extension here. And so, previous to loading your project, I would suggest you to use the SciC, that is a free software that you can perform the SegWit dump. You can see the traces, you can see the trace headers, the byte positions, the text header, everything concerning the size data previous to load, because you have to control you will see the origin of the data, kind of processing, everything will be in there. And so I will go through and give an example here. We have, for example, SciC. SciC is the software that I'm talking about. Is a free software that you can download. Is a free software, and so it's very important because he had this window here. You go to the file, select load the SegWit file, select a SegWit file, and so he will load a line this way here, and so you can select the trace header here. He will show a piece of information where your data coming from. Okay, the history of your data. Who load, who was the client that purchased the data, the processing sequence, and everything could be stored in the text header here. About the client name, the company name, for example, the crew, the name of the line name, where they come from, where the data came from, where they shoot the seismic, and so the sample interval, and so the sample traces, byte samples, recording formats, everything is in here. Now, another piece of information is also concerning the processing. If they use radon, he used radon, for example, PSTN migration, radon, stack balancing. And so there is some piece information that about the polarity of your data. That's very important to know. That's the polarity recorded SegWit standard. What it means, I will explain for you. So everything, all the piece information will be here, okay? And in the SciC, you can also apply some bandpass filter, amplitude gain control to revise the traces, okay? Okay, this is an example what we can do in SciC, for example. And so this is the information, the seed seismic line, and then you can click here, and you can display traces, and you can fulfill the colors of the wiggle traces. You can fill the wiggle as a positive. That's a SegWit standard format, and then you can also apply some processing such as amplitude gain control, weighting, or some passband filters like these here. For example, here you start to aggregate a bandpass filter, and as you see, we improve the quality of the amplitude of the data. You highlight with the amplitude gain control, you highlight the amplitude of the data. Look at this, you just put the standard wiggle field, and then here you apply a bandpass filter and amplitude gain control. Now we can see here this flat spot, for example. Here you cannot see properly, but here you can see better. And there is another issue as well. For example, here there is some diffractions, there is some mute zones, and so you pass the filter here, you can properly see some faults here. You have improve a little bit more the resolution of the data, okay? Look at this. Some reflections are muted here. There is some diffractions. And so with the bandpass filter, you can see better the reflections and some faults in here, okay? It's just a simple treatment that you start to see your data, okay? The control. And then you can, inside the SciC, you can also start to see the trace header. The trace header will show exactly the byte position where is located the shot point number, the CDP number, the XY coordinates, where is located, in which byte positions, because you will need this piece of information here in order to properly load, okay? For example, when you go to Petrel, you select the seismic here, the seismic survey here, and so with a right button, click, and so you segue import. And so exactly here, trace headers, byte position, exactly here. X coordinates 73 in byte position. Okay, it's 73. Okay, that's right. You control that. You control the trace header format here. You go here, you can confirm everything and put this information during the data loading. Okay, XY, Y77, that's okay. Shot point number, that's a 17 in the byte position. That's right, 1720, okay. CDP number is around 21, 24, the byte position, okay, 21. That is a standard format, but it's pretty good to check it out, because this is the right information that you have to put here. And then you go, okay, and he will load properly your seismic data, okay? So we was talking about polarity, and now I will explain something very important when you load your seismic data. Important to know which kind of polarity or phase you're working with, because in the end, you start your seismic interpretation, you might know which kind of polarity you're following, your horizon is following. If you are following a hard kick, a zero phase or minimum phase, okay, you might know. And so during the loading, you will see which kind of wavelet you're working with. I will explain very fast a theory of a phase, seismic phase, and polarity. Okay, there is two kind of a seismic phase. There is, when you have the acoustic impedance build up, the layer model, you have one layer that you have the wave pass through one layer and go through the second layer. And so he will make a response in this interface here, okay, interface here. And so each layer has a density and a velocity as a property. Disease has one density and velocity property, and layer two the same. And so you will calculate your acoustic impedance. The acoustic impedance is the product of the density and the velocity of a layer. And so, and then you will calculate the reflection coefficient. That is, this is the formula here. Basically, you will calculate the reflection coefficient. If you have an increase of acoustic impedance, it will be positive. That is a segue standard polarity, okay? When you have an increase of acoustic impedance in the reflection coefficient that is positive, you have a hard kick, a peak. And so according to the Society of Exploration Geophysics, the SEG standard format, the positive polarity is when you have an increase of acoustic impedance, a hard kick, a peak, okay? This means that you have a layer that the wave is going through a layer that has a higher velocity, seismic velocity, a higher density, for example, For example, if you came from a water layer down to a shale, and so the interface will show an increase of acoustic impedance, and so the seabed will be the representation of the seabed will be a hard kick, will be a peak, a black peak. Okay, this is the concept of polarity. Okay, if you have increase of acoustic impedance, the standard format of SEG is you have to represent your wavelet as a peak. Okay, not as a trough. That is a decrease of acoustic impedance where you have some soft rocks, some reservoir, some gas, some oil bearing zones. So you have a trough. Okay, and then we go through to phase. What is phase? Phase is exactly where the energy, you have the zero phase, where the energy is concentrated exactly in the central zone of the amplitude, the time zero, okay? This is exactly where we call the zero phase. The energy, the seismic energy is located exactly in the highest zone of the amplitude signal, the wavelet. And so this is a standard one. For the SEG normally uses a zero phase wavelet to represent the wavelets in your seismic section. So the minimum phase, the energy is exactly below here, is represents exactly below here. The minimum phase is not usually used. And so the most used is this kind of wavelet here, the zero phase. That is very often. When you see a seismic line, if everybody tells you, okay, this is a SEG standard format, you're seeing a hard kick as an increase of acoustic impedance, and you are seeing a zero phase wavelet. That is better, and because show better the seismic phases, the seismic stratification, the stratigraphy, the seismic stratigraphy show better the unconformities, and is why zero phase is standard used. Okay, let's go through to some signal processing that we have to do, because sometimes, as I explained before, you could have just one seismic vintage, old vintage, a legacy data, that it means an old seismic data that is sometimes that has a different polarity, has different amplitudes from another lines. This is a basic example here. For example, we have one seismic, a 2D seismic line that has a huge amplitude value here, then this line here. Okay, we are seeing another thing. We are seeing that the reflection doesn't match. Okay, but at first we will treat the amplitude gain. Okay, we have to equalize the amplitude gain related to the other line. Okay, we have to put everything in the same scale factor, in the same amplitude scale factor. In which way you can do it? You can perform. You go to one software, for example, Petrel. Once again, I'm working with Petrel, and so I will show you properly how can you make it. You can use others, because the philosophy of the other software is the same, doesn't change. We'll change the windows, we'll change for example, the operational system could be Windows operational system, or could be other one, but Linux, for example, doesn't matter. But the window will be always the same. The philosophy will be always the same. And so you can go here through volume attributes, go to signal processing, and so you choose the option trace AGC. And so you can go select the line, and so go to parameters. You can put a factor 0.1 or a 1 in order to match with the amplitude value scale to this line here. Okay, and then you apply. And now after that, you can see the same seismic line with more or less the same amplitude scale. This is very important. Why is very important? Because when you start to perform the seismic interpretation, if you have 2 or 3 lines crossing each other, and if you see anomaly here, the anomaly will have more or less the same amplitude scale, and so you can select a window between the anomaly and extract. When you extract the anomaly, you will see in your map exactly the extension of the anomaly in 2 or 3 will be important to define an area. This is very, very important. It's why I'm stressing on it. And so in the end, you have after applying the AGC amplitude gain control in this line, you will have the match, but not properly. You're seeing here, this reflector is not matching with this one. Probably they are in different phase, and you have to apply a phase shift rotation. We'll go through now. So after applying the amplitude gain control, you go in the same way, in the same line, this is the cross section here, passing through 2 lines as I explained before, the same lines, exactly the same lines. You already control the AGC. You put in the same amplitude value scales. And so you have here a displacement, a reflection displacement. So you go through the signal processing in volume attributes, you select phase shift. You select in input output, you select this line here, for example, you have to match with this reference line here. And then you select an angle, because when you perform a phase shift, you have to choose an angle in order to invert the position of the reflection. You put 45, 90 degrees, in this case, 108 degrees, in this case here. You try to 45, 90, 108, and so you will, after that you apply, and you will see the match here. Now, it's, you match properly. You make a correction, and so now the data are adjusted, so you can follow properly, and so you can extract, for example, this anomaly here, and so you have in your map the extension of the anomaly. It doesn't matter if this survey is different from this survey here. It doesn't matter the vintage. The most important is that they are balanced in amplitude scale, in polarity, and also in phase. They are matched, more or less matched. And so this gives more reliability to your data. And so if you show this to your exploration manager, okay, for sure you need more lines over that. This is a way to convince your manager to purchase more seismic lines, more data, okay? If you have a good extension of anomaly, it's a good way. So after that, we can start the seismic interpretation. We have to tie your seismic with the wells that you already loaded. And you need a synthetic to properly tie your well to your seismic. How you can build up a synthetic? This is a piece of theory that's very, very fast. You have to grab a sonic log in order to extract the velocity. You have to select a density log in order to obtain for sure the density. And then, as I mentioned before, the acoustic impedance is the product sonic times density, that is velocity times density. And so you got your acoustic impedance intervals. So after that, you calculate your reflective series, the reflective coefficients here, the reflections, the boundaries of your layers, and then you convolve, you make a algorithmic operation, and then you choose a reference wavelet that could be a zero, that is always a zero phase, a Richter 30 hertz, for example, or 25 hertz, and then your synthetic will be, seismogram synthetic will be ready. and then you will start to perform the time shift with your seismic traces. And when you perform this time shift, you properly load, you properly match your well, your seismic markers, your logs with your seismic, okay? This is the basic way to properly match. The most important is to have this, to keep this in mind, because the synthetic will tie your seismic with your well, and it will be important to follow the correct horizons, okay? Because this is very important to show to a man, okay, this is the unconformity, tertiary unconformity interval, or upper Cretaceous, or top rift. And so if you have a properly, everything match better, okay? And so is the way to, in petrol, to build up a synthetics, okay? You can select one line, you can select the logs here. Okay, this is the wavelet, the seed Ricker 25 hertz, that is this one that you normally use. You can put this as reference. You select a sonic from your well and a density from your well, and then you produce your synthetics. And then you load in your well and you perform the time shift to properly correlate, because you can correlate peak by peak, okay? So this is an example of synthetics here. This is a synthetics, and this is a seismic line, and this is a good match. For example, we have a hard kick here, and so you have a good match of the synthetics between synthetic and seismic line. And so another hard kick here, a hard kick in the seismic, and a hard kick in the base, and so you have the soft zones here. And so look, this is a good match. And you're seeing the density log, and so the low density is where you got some gas here, and so you have a low density and low velocity here. So you have the markers very well calibrated, and so you can see where the reservoir interval here, okay? And so it's very important, because you will make a regional correlation. This is very important. And so you start to perform, after you load all the wells, perform the synthetics, you can go through with the regional seismic interpretation. The seismic interpretation is very important, because you will see in a very huge view where is the basement highs. For example, in the gravimetric map, you will see this anomaly where you got the high, the lows. And so you will map for example, the basement here. After you conclude your well logs correlation and cross sections, well cross section, and logs correlation, well correlation, you will start to perform the regional seismic interpretation here. With well ties, you can spread station here, and then, for example, you perform grids. And you see, okay, this is a basement high, an important focal zone. This is an important kitchen here, for example, and then is a good focal point for hydrocarbon, for example, here. Okay, this is an example that you can start to see the possibility of success. Where is the lows, where is the highs, where is the kitchen zone? It's very important to start first with the regional interpretation. And then, after perform the regional, you go through here to make a surface, and then put in a convergent interpolation, and then you produce your surface, a regional surface, for example. Okay. And then after, to build up all the surfaces, you have to build up, if you're working with the 2A time data, you have to create a velocity model data in order to convert the 2A time data, the grids, into depth. You have to build up a velocity model. How can you do it? You have to, for example, this is petrol, once again, advanced velocity model. You have to grab check shots, that is velocity, well velocity data, that's very good data to use. Markers to make the control of your velocity model. You could use also a seismic velocity that you can use the seismic velocity and transform into Dick's formula in interval velocity. And so we have to use properly this data, the seismic velocities combined with well velocities, surface peaks and grids to control your velocity model, okay? And so there is a lot of tools that you have to choose at first, all the layers to choose which kind of velocity we're going to use, which kind of data. For example, the first layer here, you can use a constant. This is the first layer is the seabed, the sea level. This is a seabed here, and so you can put, for example, a constant velocity such as 1,500 meters per second, for example. You can put a constant interval velocity here. That's exactly 1,500 here. And then you can put another layer here, another surface here, and so we can calculate the interval velocity here. And so we can use the well tops as a constraint, and also can use the well velocities as a main velocity information. And so we can use which kind of velocity equation, Dick's formula, a linear equation. And so will be the model if you use wells, a surface to calibrate your model. In the end, you got this. I put a seismic interval velocity, a velocity model draped on the seismic line in order to show you the control. After that, you have this is the interval velocities of each layers. And then, for example, in the basement, you have a pretty high velocity, about 5,000 meters per second. And then here you have about 2,000 meters, 2,000 meters per second as velocity. And so you will see the distribution of the velocity, okay? And it's respecting the surfaces. And then after build up the velocity model, you can convert all the two-way time grids in this region in depth, and then you start to define your lead, your prospect. For example, you have a lead here, a prospect here, and so you have to match here. Okay, you can grab this one, make an interpretation of this zone here. If you believe that is a prospect in time, you create a surface in time and put inside this velocity model, and so he will convert into a depth grid. And so you can start to calculate your volume, your gross rock volume, and so I'll show after, okay? And let's go to the best area best area that you like, that is a seismic interpretation. But you have to go after performing the regional seismic interpretation, you will start to see some seismic phases that is related to reservoir for sure. And sometimes this is some examples of kind of reflection that you're gonna see, plumb parallel, continuous with high amplitudes that you could have some limestone in here, gradations, and so not so good for a prospect definition. But sometimes you can see some seismic phases related to mound shape, related to carbonates. That's you have a mute zone inside, and you have a hard kick over that, an increase of acoustic impedance here, and so you can see a mound here. That is something related to carbonate buildup. That's important because there is some that the carbonate buildup could be important seals, but could be some related to some reservoirs, related to some oil fields. So another one is chaotic, is related to carbonate buildup, that is reef zones, for example. And so we can see some mounds here, and we have to keep sure that we are seeing this kind of environment. And then you have the chaotics, that is, you have some wavy, some lenses that relate to more with siliciclastics, okay, mass flows, so important as well. But if you're dealing with with carbonates, with carbonate plays, you have to take care or follow more or less these two kind of pattern here, the B and C. If you are working with carbonates, carbonates, prospect carbonates, but if you are dealing with silicic clastics, I would suggest to take care with that. The progradational phases, the longitudinal, when you have the, for example, shelf edge delta, for example, here, you have upper slope channels and some lobes here. And so the seismic signature, the seismic phases, normally, when you have this kind of progradation here, you can see some sigmoids pattern here, amalgamate sigmoids, and so a progradation zone. And then this is exactly the slope channels feature. That is a several sigmoids pattern that's pretty good to see. Okay, that you're seeing a delta or a channel slope environment, and so and then you can see some lobes here. In the end of the sigmoids, you can clearly see some lobes here. That's related sometimes to a slope for flan in Santos Campos Basin, the turbidites, the famous turbidites of Campos and Santos Basin, that has some slope for flan signature here, this mount signature here. And so if you cut in a transversal, if you perform a transversal cut in these lobes here, you will see exactly these features, these wavy features here, the wavy and some lenses. Okay, some lenses, that is very important to see that, okay, we are dealing with some lobes, with amalgamate lobes. This is very, very important, silicic clastic deposits. And so this is a main important seismic signature concerning silicic clastics. And so you have to take it in mind. If you're working with silicic clastics, this is the two important patterns to follow, okay? So this is a base case prospect. For example, we have here one example of Foz do Amazonas in Brazil, in equatorial margin, that we have this four-way closure structure here in that map. And so we have this reservoir in Miocene here, an amplitude value here, but we can see some seismic phases here concerning channels. There's a tertiary channels related to deltas. And so this environment here, we can clearly see some lines here. And so you have some a structural element here that's quite important. A fault that could be a migration, a charge pathway. And so it's a good prospect because, okay, we have more or less the reservoir facies, we have a seal because interbedded seal, we have a stratigraphic trap because it's interbedded seal, and also we can have a structural trap. We have a structural trap, a four-way closure structure, a combined trap is pretty good, okay? And the source rock is down below, and so we have some faults here that could be the charge. That is a good concept of petroleum system and prospect that you're using here. And then you can define the area of your prospect in a structural map. For example, here we have 45 square kilometers, and then we define more or less 20 meters of net reservoir. Okay, we have the phases here. Seismic phase concerning the silicic clastics, and so after that we can calculate your prospect. Okay, the prospect definition. You can use this formula for oil base case and gas base case, and so you calculate the area where you got in the map, the net pay, the porosity of a closest well, a petrophysical data of the closest well, and so you got everything and calculated your oil, original oil in place and the prospective resource, and so you got your prospect, your volumes. So you have the prospect here, but then you have to risk your prospect. You have to risk the resource in order to show it to a manager, because you have to aggregate the geological risk in order to show to the peer review in order to be ranked. The prospect will be used. This is the reference value, the prospective resource. Okay, when you have the recovery factor, apply the recovery factor. This is the reference of your prospect. But for ranking, you should use the chance of success, the risk, the geological risk. You have to put this chance of success, for example, is 19%. You put times the prospective resource, and so you got the risked resource. This value here will be used for ranking, prospect ranking, okay? And so the peer review will be used, is a technical team that will judge your prospect, your lead, in order to see if you use the correct petrophysical parameters, if you follow the correct horizon, if you perform all the stuff correctly, and we'll judge and we'll see and we'll aggregate value to your prospect or not. Okay. And after that, they will try to judge your initial chance of success and try to analyze with amplitude values, if you have a DHI, direct hydrocarbon indicator, AVO, and other stuff. And so he will try to penalize your prospect, okay, to judge better. And so he can give you, okay, now your chance of success is 17. You can judge, you can revise all the petrophysical parameters and try to judge the risks, okay? And after that, when you show to your manager, you have to properly find out an analog. An analog, for example, if you have a slope for fun, if you define a slope for fun, a turbidite in there, you have, for example, Roncador in Brazil. Roncador is a famous field in Brazil that you should use as a mirror, in order, because no one doesn't know your prospect, but everybody knows Roncador, for example. And the analog might be the same that have, the analog might have, the prospect might have the same depositional system or similar and the same age of your prospect, in order to make a correlation, in order to defend your prospect, because the managers and the board of directors might know which kind of oil fields or opportunity they are facing, okay? This is the analog, the depositional system, where is related your depositional system. And so there is an example of important analogs. If you're defining pre-salt plays, okay, 2P could be a good analog. For example, if you're working with carbonates or with a tertiary or four-way closure, something similar to the depositional system of Goa, you can use Goa, for example. And then you have to match your view with your exploration manager. Show your technical presentation in order to be approved in a board of directors. Okay. And you have to take into account about the prospect might have the minimum economic prospective resource of a related basin. So if your prospect, for example, your manager can say, okay, you're working with a equatorial margin, you have 100 you have to find out a prospect with 100 million barrels prospective resource. In this case here, you find 172 million barrels as prospective resource, is inside of the minimum prospective resource given as reference, is inside. So the prospect is good. Okay. And then you have to take care about the break-even, the costs, the break-even, that is the minimum economic for your basin produce, for the company has money to produce the value of the US barrels. If the US barrels stay in $25 US, onshore Middle East will be economic For example, we are now in 60 US dollars the barrels, the cost of barrel. So the offshore shelf will be ready. The onshore routes as well, the heavy oils, you can go to this place, okay, to present. The onshore hassle roads, okay. But if you go to Arctic, 75 is still non-economic to go through, to choose this opportunity. And this is a forecast of the forecast of the oil prices, okay, in the West Texas WTI, that is quite the same of Brent, but the forecast is to keep the oil price in 60 US dollars the barrel. And so this is important numbers to keep in mind, okay? If you are in Arctic, okay, I will start to work with Arctic, it's not probably the good time. Better to choose Middle East, better to choose offshore shelf, better to choose onshore roster, or something that is a good reference of break-even. And also, some companies has a reference break-even, the minimum economic to invest, okay? That is about, the rule is about 40. When the basin has the cost of barrel is about 40 US dollars, the break-even is about 40 US dollars, is okay for some companies to invest. Is an example of Exxon, Shell, Conoco, Chevron, Pioneer, other companies. And so this is for 2020, this is the break-even for the oil companies. We might take care with these numbers because all the board of directors will think about it. In the end, this is the decision tree of all the steps. The most important step is this one here, where the geologists and geophysicists are included. Okay, lead to prospect definition when you start to load everything, and so you define your prospect. The peer review will make the technical revision of your prospect. After that, you got the final numbers, authorized final numbers of your prospect, the final volumes, the final risked volumes, and then your prospect will be judged in a regional ranking, taking into account your risked prospective resource. And so the manager will take care with all the steps, will judge all the steps, control all the steps, and then after approval of your prospect, you will pass through a board of directors gates that it will be taking into account the economic truncation such as oil prices, British thermal unit price of gas, and so break-even, budget, CAPEX, and everything will be, your prospect will be truncated to your volumes will be truncated into these values here, and then if he could be approved, ready to this, your prospect will be ready to a bid round. The board of directors will say, okay, you're ready for bidding, you're ready for invest and put money in this block, try to bid and win. This is the philosophy. It's a very simple way, but all companies follow more or less these procedures. The unique difference that change the names, for example, some companies, some use peer review or technical review, or that is a bunch of guys from other countries, other basins, other branch of the company that will judge your prospect. So it just changed the names. For example, here in some companies naming gate 1, gate 2, or economic gates. That is the philosophy is the same. And so the final conclusion is the G&G data loading, controlling, gathering are very important to give reliability to your project and to the peer review, because if the peer review seeing that you're using different petrophysical data without reference, without any confidence where the data comes from, he will penalize way more your prospect, okay? And so the G&G staff might be aware about the economic indicators, especially the minimum prospective resource that will be taken into account in one basin. For example, the minimum prospective resource is 100 million barrels. And so you cannot find nothing less. If you find something less, the manager will say, okay, forget this prospect, forget this lead, go through to another one that have at least 100 million barrels as a prospective resource. This is the philosophy, okay? So I hope